So we'll wait for 2 3 minutes, then we'll start the session today.
Sir,
Yeah. Yes.
previous weeks, where can I find the links? I'm not able to get the links for
Previous
it. Just previous recorded sessions of week 7 up to week 2, week 8.
previous week lectures. Yeah.
Problem sessions you contacted me, sir. I
Uh,
didn't find where I have to get.
you
Could you
didn't
please
get the
post it?
you didn't get the links.
Yes, sir.
Links that I have posted that YouTube channel link on that discussion forum. So
Sir, if you don't mind, can you post one second?
yeah. Okay, I will post it again. Okay, I will write it so I will not forget it. Uh, YouTube channel link. Yeah, I will post it again. Huh. So okay, I think I will start with today's session. So we will be discussing about what we studied in week 8 session. Uh, Welcome to the course Open Practical Applications, Design Simulation and Implementation. So before that, just we'll go through what we studied in last week, week 7. So week till week 7, we completed this design and building of a temperature on-off controller, where we saw that what is the control scheme and what are the components and blocks used in that controller for a temperature on-off controller. Like we use controller, heating plant, sensor, and signal conditioning circuit, as well as error inputs. So this was the whole system. So we studied, then each by each we try to implement what each block will consist of, and we realized that using opamps. So like for implementation of error detector circuit, we use a differential amplifier here. As similarly for then we also use signal conditioning circuits for our LM35 temperature sensor in order to maintain the sensitivity as what we required. Then we saw heating circuit and how we can make heating circuit using a transistor and why we needed that op amp. So that all we studied last week. So then we also talked about the power dissipation factor of a transistor and how we can convert that into the temperature. Then we came to controllers like on-off controllers, proportional and proportional integral controllers, and we saw how we can realize each and every type of controller with op-amps. Like on-off can be realized using Smith trigger, and then we saw that how this proportional controllers works by taking the analogous this examples of a wall system, water wall system. And then we realized this with using opamps, different sets of opamps, and then we use proportional integral controllers also and how they work. And then we added both integral and proportional controller, and we realized this proportional integral controller. So yeah, that was all about week 7 session. So today we will move ahead with some different applications of opamp. So the first application which we'll be learning today will be to design and build a signal conditioning circuit for the thermocouple. So to compensate for temperature correction. So today we will be talking about this experiment. So it is to design and build a signal conditioning circuit for the thermocouple to compensate for temperature correction. So we will be looking how why we need this compensation for temperature correction in thermocouple and what these thermocouples are. So as we studied in this lecture that so basically thermocouples, if we talk about thermocouples, so this is a sensor which we can say sensor which measures sensor to measure temperature. Okay. So what this thermocouple consists of? So it looks like something. So there are two metal wires which are connected at one end. So this we can say junction one, and the rest of these two ends are we can say junction 2, and this is a reference junction. So basically there are two junctions, and if we heat one of the junction, then there will be uh, temperature gradient throughout these two wires, and these two wires are made of different metals, metal A we can say and metal B. So according to that Seebeck effect, and because of their different metal properties, they will be producing different voltages at these junctions, at junction J2, that is V1 and V2. So if we can somehow measure these two voltages V1 and V2, either using a voltmeter or anything else, then we can get the idea about what is the temperature here based on the reference temperature which we are giving at J2. So that equation is given by V naught equals to uh, alpha. It is T temperature at J1 minus T reference temperature at J2. Okay. So this alpha is basically the sensitivity constant we can say, or Seebeck coefficient. This is Seebeck coefficient. So this is
To
there.
maintain the reference temperature constant, we will connect LM35 also simple circuit.
Constant.
To maintain the reference temperature
Ah,
constant, we will connect what I mean any environmental factors that will affect the reference temperature. That's how
your
we connect
voice
one
is
more.
breaking. Can you be clear, or you can write also, if possible. Uh,
Yes, to maintain the
uh, to main,
reference temperature, room temperature constant.
I'm not able to get. Your voice is breaking. Uh, can you
I will
write? Can you?
message.
Yeah, yeah. You message. Yeah. So yeah. So this is what thermocouples are. So there are like so these thermocouples can range from minus 200 degrees Celsius to 2000 degrees Celsius. Okay, so they are made of different thermocouple alloys like iron constantan, copper constantan, chromel alumel, and chromel constantan also. So these are different type of alloys which we can make these thermocouples from, and accordingly we can set their ranges. So now why then now the question will arise, why we need this compensation in this thermocouple. So what happens actually, so we will analyze why we need compensation in thermocouples. So we have this hot junction, we say the J1 junction, we can denote it as the hot junction. This is hot junction, which is basically where we are trying to measure the temperature. So this is where the temperature is being measured from. Then we have two metal strips. One is metal A and another one is metal B. So there will be, because of their different metal properties, there will be some voltage, and these are being connected to a junction here, cold junction we can say, or reference junction. This is, yeah, to maintain reference temperature constant due to environment in order to measure them. Yeah. Ah, yes, yes, LM35 to see the reference temperature. Yeah, we use LM35s. I will see in the this coming lecture that we use LM35 for measuring this reference temperature, and by that we will correct that also, that issue will also, we will compensating that actually the effect of reference voltage. So we'll see in this lecture. Yeah, you are right. Okay. So this reference, this is a reference junction. Hmm. Yeah. So this we also say as cold junction. Okay. So now if we can extend some leads, copper leads from here, copper and copper. So but then we can measure the V output voltage, and this V output voltage, as I said, that this depends on this equation. But then now there is a need to maintain the temperature of this cold junction, this reference junction. Since this is a reference junction, so the temperature should not vary. So easy way to easy way to measure the temperature of the hot junction. Measure the temperature of hot junction. That is junction J1. This one J1 is by maintaining the temperature of this cold junction as 0 degrees Celsius. Of this cold, okay, that pages. Hmm. So it's by maintaining the temperature of the cold junction as 0 degrees Celsius. 0 degrees Celsius, and that is can be done using an ice bath. So ice bath is basically we can say ice where, like we can easily say that where the ice we can use, and this junction, reference junction, we can dip here like this. So this is the hot junction, and this metal wire is metal A, and we have this metal, second metal, and we are then using the V output plus minus V output here. Okay. So this we can do, but this is ice bath. This is a good standard reference temperature for 0 degrees Celsius. But then it is difficult because for some time we can. So why it is difficult? As this is impractical. This thing is impractical. As this cold junction will not remain, as cold junction will not remain at exactly 0 degrees Celsius. So there will be some variations when we'll be using this ice bath, or yeah. So then if our reference voltage will change, reference temperature will change. So there will be some according to this equation. So we will be we'll be seeing some effect on that our voltage output also. So that will not be constant. So we will not be able to determine the hot junction temperature. So now what we can do? So thus we need some compensation. Thus we need some compensation technique. Thus we need some compensation technique to account for the voltage created by the non-zero cold junction temperature. So it basically, since this reference temperature will be changing, so accordingly this V out will be changing. So for that we will be needing some compensation. So for this, for this, what we will do now, as you said, LM35. So we can now use any of the some sensing mechanism, so that we can continuously measure the temperature of this cold junction, so that and we can develop some techniques so that this cold junction temperature, which is being measured continuously, can be feedback or can be added to our original output, so that it can nullify the effect of changing this reference temperature. So we can use some temperature sensing mechanism or sensor, that is like RTDs, we know, thermistors, some silicon ICs also. Okay, so so that's why we need the compensation. So that's why there is a need for this compensation requirement in our measurement, in our cold bath junction, or we can say cold junction. Okay. So now we'll see how we can realize this compensation, and also before that, then we now before that so we will discuss that simultaneously we'll solve a problem that was being solved in that lecture also. So problem was like, so we have a K type thermometer, thermocouple, sorry, and it is to be we need, and for from this thermocouple we need an output of 2 volt at 200 degrees Celsius. So this is a requirement that when it is showing 2 volts, that means the temperature at the hot junction is 200 degrees Celsius. Then the question, then they are asking that to design a signal conditioning circuit. So we cannot get this 2 volt directly as 200 for 200 degrees Celsius. We will be using some of the circuitry. Then we'll see how we can use that thing. So basically, the question is asking design a signal conditioning circuit for this thermocouple such that it can compensate for temperature variations at cold junction. So we just came to know, okay, there will be some variations in cold junction and we need to compensate it. So here we will be now designing what can be the compensation for that thing, how we can compensate that changing reference temperature. Okay, so they are saying this. Now there is one more constraint, we can say. So sensor has Sensor has three terminals. So one supply voltage Vs, then output voltage Vb, and third terminal which is grounded. So this is the sensor which we'll be using to compensate for using for the compensation uh, sensor. So this is the requirement for that. And output voltage varies at 10 millivolt per degree Celsius. Okay, so for this the output is varying at 10 millivolt per degree Celsius. Now for our thermocouple, if we talk about our thermocouple, it has been given that it is K type thermocouple. K type thermocouple. We are using 0 degree Celsius reference at cold junction, and it has to give an output of 8.2 millivolt. It gives actually the output of 8.2 millivolt at 200 degrees Celsius, and its sensitivity is 41 microvolt per degree Celsius. Okay, so now we have a question in front of us, like K type thermocouple is there, where the output what we require is that is 2 volts for 200 degrees Celsius, but we cannot get directly because the thermocouple, this is the thermocouple readings, that is the specifications, that it gives 8.2 millivolts only for 200 degrees Celsius. Its sensitivity is 41 microvolt per degree Celsius. So now we can simply say that since that 200 degrees Celsius for 8.2 millivolt, it is being given by this thermocouple. So we can straight away say that at least we will be needing some amplification, some amplifier we will be needing, so that we can scale it to 2 volts at 200 degrees Celsius. One thing. Now another thing is that we also need to compensate for the changes in the reference temperature. So we need two things. So one, amplification; second, compensation. So how we'll do that? We'll see. First of all, in order to, like, we also saw that we should be having the same sense. So whatever sensors we are using in a system, we should try to maintain their sensitivity same. So but why we need that actually, we will see that also as the sensitivity. So first of all, we'll try to see what can be the sensitivity. So what the gain factor will be required for this thing. So gain of first differential amplifier will be chosen such that the response of two sensors are made equal. Okay, so they are made equal. Now what is gain? Gain will be the sensitivity of second sensor, that is, this is basically what we will be using here as LM35, and the divided by the sensitivity of first sensor. Okay, so this will be, as we know, we have been given that the sensitivity of the first sensor, this LM35 is 10 millivolt per degree Celsius. So we will use that divided by the sensitivity of the thermocouple, that is 41 microvolts. So we will get approximately 244, um, the value of the gain which we require for our circuit. So now, how we'll develop this? So first of all, yeah. So why we needed this sensitivity correction? Why we want to have this? We say this to scale this up for to match this sensitivity. So let's say we'll go with some simple example. Let's say we have a set temperature, that is the reference temperature, 0 degree Celsius. Okay, reference temperature, and our hot junction temperature is equals to 100 degree Celsius. So the output will be what, since we have this 41 microvolts of, it is equals to, we can say, 41 microvolts into this temperature 100 minus 0 into this one, 0 into 10 millivolt. That is, this is the sensitivity of our LM35, which is used as compensating sensor, and this is the sensitivity of our thermocouple. So what will happen? So this output is basically, we can say, directly proportional to this value. Basically, the temperature that is being when we have a reference temperature of 0 degree Celsius. So the temperature measured, the basically, yeah, the output measured by the thermocouple, and the this output by the RLM35. So what will happen? It will be directly proportional to 4.1 millivolt. Okay, we got this. Now, if we have set temperature equals to 10 degrees Celsius, that is reference temperature, that is reference temperature, and unknown value of temperature is now 110 degrees Celsius. So now what will happen in this case? Here also output will be what, 41 microvolt into 110 minus 10 minus 0. Okay, 0 into 10 millivolts. So here also we will be getting 4.1 millivolt. So we observe that the temperature which we want to measure for like some junction, if it is 100 degrees Celsius in first case, or it is 110 degrees Celsius, and the reference temperature is 10 degrees Celsius. So if the difference is remaining constant for junction J1 and J2, then we are getting the same output. So we cannot say whether it is 110 degrees Celsius or 100 degrees Celsius. That's why we need this. There is a requirement of making this sensitivity same for these things, scaling the sensitivity so that we can get the different outputs for different hot junction temperature, irrespective of this reference temperature. Okay, that's why we made the sensitivity of both the thermocouple and the LM35 same.
So,
Yes.
so if you don't mind, can you put sir, for we guide the same question this one. Question
uh,
5 and 6, I'm not able to sir, get an idea. Sir. Could you please
Question
inform me, sir,
5 and
if you
6
don't mind.
of assignment.
Yes,
uh,
weekend. Yes, sir, deadline has been passed.
yeah, 5 and 6. Yeah, this one and this one, na. Yeah. What is your doubt? What is your doubt? What is the question again? Hello.
Same thing, sir. Same thing, sir.
If you can
I
write,
mean,
because you're
that I'm not getting the
huh,
5 6 question.
you're not getting the
Question 5, I'm not getting idea, sir.
question
Question
5.
5, idea. Question 6, yes,
Okay,
sir.
question 6 you were able to do.
With the table, how can I get
So
I know,
so
sir, well, you said a little bit about the question 6. No? I can able to get the point.
Your
Still, if you
voice.
have time, means solve this
So
question
what
six.
I'm getting is, yeah, you are able to do
So I
question
get a good more
five.
idea.
You are not able to do question five.
5 and 6
Five
question.
and six, na? Okay.
Yes, sir.
These are having doubts, na?
Yes,
Yeah.
sir.
Actually, question five I solved, so I was able to solve. Question six, I am getting some different answer. So if any one of this, any of one of here present, if they got the correct answer for question six, they can say. Because I tried this, I tried with different methods also, but I'm not getting the answer for this question six. But yeah, question five, yeah, we'll see. Question five is fine. So if you were able to solve this
Sir,
question six,
question 7, sir.
question seven. This
Sir,
is
question 7.
this is easy.
Yes,
Yeah.
sir. Like,
Yeah. Tell me what is your doubt?
yes, sir. My question is, uh, I
Can you
get the answer as 1
increase
plus R as
increase your
same,
voice?
same thing.
Increase. Can you increase your voice?
Okay, sir.
Huh.
Okay, sir. Okay. Can you hear me, sir? Now?
Yeah. Tell me.
Sir, my doubt is, yes, sir. At the non-inverting terminal, the resistor is in series, so that won't make any effect, sir.
Yeah. This resistance. Yeah. It will not have any effect.
Actually, it is in series, no, so that's not that.
So you are saying this is in series, so it will have effect or something. You are saying like that.
Like, yes, sir. There is a voltage divider, no, sir. But in series, the voltage difference between them.
No,
That's
no.
how
See
that, sir.
here, since we are considered, say if nothing is mentioned in the question, then this is an ideal diode. So if this is an ideal diode, then no current will flow through this terminal. Okay, non-inverting terminal. So if we use R or we don't use R, then it will not affect our answer. Getting my point?
Yes, sir. When will you make a sense, sir? Means when will that resistor will matter, sir? If it is ideal case,
Ideal case. But see, if it is a practical case, then what will happen?
it is practical.
If it is practical, but we don't have to consider here in this case this R. But if it is a practical case, then what will happen? There will be some IE bias current. Okay, at positive terminal, IB plus we can say. So what based on this IB plus, there will be some voltage drop at across this register. That will be, we can say, plus minus. The voltage will be what, IB plus into R. Huh? So this voltage will be seen in at this terminal because of virtual short. So here we will get VI of S plus IB plus R, something like this. Okay, we'll get two voltages here. So based on that two voltages, we'll have to identify what is V naught. So this is basically, then V naught will be depending on IB plus and V input also. But since this is a practical case, we don't want to consider this IB plus. So is it fine?
Yes, sir. Sir,
है ना?
would you refer
हाँ.
any books, sir? I'm referring for the exam of the final exam.
Okay, so I will drive this practical
Any
case
reference
also.
books, sir?
Okay, I will drive. I will drive this question based on the practical case. So what will happen? We'll use superposition principle. We in first case we have this minus plus this capacitor. We have V naught. We have nothing here. We have only R, this C. So there is IB plus. Okay, IB plus is here. Because of that, there will be IB plus R. It will be here, but it will be negative because current is flowing here. The drop will be like this. So the voltage drop will be here, negative IB plus R. So based on this, IB plus R by R. So huh? Raised hand. Okay. Yeah, Manish. Yeah, you can tell me.
सर ये नॉन इन्वर्टिंग ओपन है ना,
Yeah. Yes.
तो इसका ट्रांसफर फंक्शन मींस गेन हो जाएगा सर, 1 + RF/R1 कर दो ना सर।
One plus RF
वन
upon. हाँ. That is
आर
fine.
वन
That
आर एफ में 1/SC रख दो और R1 में R रख दो, हो जाएगा सर सॉल्व।
RF में
1/SC
RF में.
कैपेसिटर है सर, हाँ,
हाँ. So
RF हो जाएगा 1/SC,
1/FC.
SC है ना सर, और
हाँ.
R1 R है आपका।
Uh, no, no.
R1,
I was telling him about this thing. You are just using this.
1 plus
Then
it
also we can simply
1
say,
plus
see,
RF upon R1, sir. Put it into 1 plus RF upon R1.
one plus this one will be what? R this one be one by SCR. You are saying like this, na?
हाँ सर, इसको सॉल्व कर दो, हो जाएगा सर.
Yeah. That is a simple. Yeah, that is the easiest way to do this. So what will happen? This will be V naught one, V naught dash. We can say. Yeah, you are correct. This will be V naught. Then we will have V naught double dash. That will be because of this one. Vi of S 1 plus SCR. So now if we add both of this, we will get V naught 1 plus R, or we can say Vi of S simply plus Ib plus R 1 plus 1 by SCR. Okay, but as in this case we won't be able to then see, because of this bias current we cannot get the expression for this transfer function, as we won't be able to get V naught and Vi separately because this is there. Okay, so this will be practical, but we don't have to consider this thing. This is not required, but just for the understanding, for the practical case, I was telling this. Okay, I think it's fine for this Thalpasai.
Yes, sir. Sir,
Oh, okay, okay.
sir, could you, I'm appearing to final exam also.
Uh-huh.
Sir,
Yeah.
sir, could you give any reference books, sir? Sir,
Reference
professor gave
book.
10 books, no,
Acha,
sir. I'm
reference
not.
book.
Yes, sir.
You can go for from which I made questions, and I really like that book. That is Sergio Franco. I don't know from where these questions will be there for you in the final exams, but I really like this Sergio Franco opamp designs and
It should cover
applications.
entire.
Huh? Your voice is
We should cover our entire lecture, sir.
entire.
Sir, it will cover entire weeks.
Yeah, it is there. Like
Entire
everything
weeks.
is there about opamps in this Sergio Franco. Opamp practical, something is there. Opamp applications or something. It is only about opamp applications. Then there is this one chapter in this one, Cedra and Smith, that you might be knowing, maybe knowing Cedra and Smith. There is one chapter of opamp that is somewhere, yeah, eight chapter or something. That is also okay. So these two books are fine, but this Sergio Franco is little more into depth. So you can study about opamps in depth. But then just for the overview and all of this, it's Adrian Smith is fine. Okay. So these two books are there. So yeah.
Thank you, thank you.
Uh, so
Thank you so much, sir.
yeah. Okay. So now we were looking for this one. So yeah, anyway, you are here, so you may be waiting for this assignment questions only, I think, because if you have any doubts
Five,
in
fifth number question, please.
fifth na, so
Yes,
fifth
sir.
how I solve. So see, it is given a thermocouple is selected to provide an output voltage for a given temperature. The corresponding output voltage for a differential temperature is shown in the table. Okay, while considering the reference temperature 0 degree Celsius. So here for all of them 0 degree Celsius is the reference temperature. What is this? Wait, something. Okay, sorry for that. Yeah. So it is this is 0 degree Celsius reference temperature. Compute the differential output voltage from the sensor for a reference temperature of 5 degrees Celsius. If the specimen temperature is 50 degrees Celsius. So now we have the hot junction temperature as 53 degrees Celsius. We have this reference temperature for this measurement as 5 degrees Celsius. Okay. So now we know the sensitivity. Sensitivity is what basically, if you make a graph, it is like uh, so we are saying this is what temperature on this is basically sensitivities are uh, yeah. So it is here it is the output voltage and here is the temperature difference. So this is the characteristics. This is the output characteristics of an thermocouple. So based on the temperature difference, it is like based on the temperature. Basically, we can say this V naught changes. Okay. So sensitivity is basically the slope of this output curve. So we can say sensitivity is equals to change in the voltage, output voltage divided by change in the, or we can say the temperature based on with respect to the reference temperature. So if we use this formula, then how we can solve this question? Then it becomes very simple. So we have so in this one 53 degrees Celsius. Okay. So we need to find what complete differential output is of the sensor. Okay. So this will be since sensitivity will remain same. So it will be 53 minus 5 is the temperature. Output voltage. Okay, so we need output voltage here. So this is for the case of when for the second case. But based on the table, we have the output. Let's say if we consider let's say these two voltages, then it is 42 minus 32. The change in the voltage divided by the change in the current. Okay, this is what sensitivity is. So this is given in the table here. The change, we can say the change for 10 degrees Celsius, there is a 10 microvolt of change. As you can see in the, you can read that by this table itself. So based on that, we have 10 by 10 microvolts per degree Celsius. So we have basically 1 microvolt change per degree Celsius. So for if we need, so this is V output by 53 minus 5. So we got this 1 microvolt per degree Celsius change as a sensitivity. So we can easily get one V output voltage as 1 microvolt into 48. That will be 48 microvolt. Is it okay? And
Okay, sir.
Hana? So yeah, so you need to know okay what is the sensitivity if it is not given. So it is basically how much voltage change is happening based on per degree Celsius change. So yeah, so based on that we can calculate this thing. So now okay, so yeah, this question I was not able to solve. So if you were able to solve, then you can tell me. Sixth question. I am getting the wrong answer for this. If anybody was able to solve this. Acha, okay, no. So anyway, I will tell my approach. So how I approach this thing. So thermocouple with a reference of 0 degrees Celsius shown an output voltage of 0. So it is showing for a reference of 0 degrees Celsius. Okay. So it is for just hot junction temperature is 25 degrees Celsius, and the output voltage it is showing is 0.8 millivolt. Now, the Seebeck coefficient they have given that as thermocouple coefficient, that is alpha equals to 52.17 microvolt per degree Celsius. So now if we solve this like we have 52.17, then we have 25 and 0, 25 minus 0. If we solve this, then it will not be equal to 0.8 millivolt. It will be somewhat less than that. So I think no, it will be I think more than that. This thing, this is microvolt. So there is some I think attenuation happening or some op-amp some amplification is there. Let's say we have that A factor. So based on this amplification or attenuation, we are getting the 0.8 volt. Then it can become equal to 0.8 volt. Okay. Then compute the unknown temperature. The output voltage is 2.5 millivolts. Compute the unknown temperature. The output voltage. Now, since we will be able to calculate A from this, then what we'll do? Now we have 2.5 millivolt as the output equals to. So when the reference temperature, now they have given reference temperature as this. So we don't know the hot junction temperature T minus 25. We know the sensitivity 2.5 microvolt. We know the A value from this equation. So based on that, we can calculate the T. So for me, T was some 100 degrees Celsius, some 101 degrees Celsius. It was coming. So I will maybe I will look more into this question and then I can tell okay what is the actual thing.
Hello,
Yeah,
sir.
yeah.
This is Ramamurthy.
Yes, yes. Tell me.
So I have tried some other way. So I
Yeah,
think
tell me.
okay for that. So let us consider for 25 degree centigrade, the
Mm-hmm.
output is zero point 0.8 millivolt.
Okay.
So whereas uh, in another case it is 2.5 millivolt.
Okay.
So the reference is different in that
Uh,
case.
T
So
minus
with
some.
respect to,
Uh,
we will add 2.5 plus zero point 0.8. We will get 3.3 millivolt.
3.3 millivolt. Okay.
Then we will divide by that Seebeck coefficient, like 52.17 microvolt per degree centigrade.
Hmm.
In that case, we will get 63.25
So
degree
this is
centigrade.
equals to T minus 25 equals to 3.3 milli divided by this 52.17.
Is it right?
Okay.
Because everything is with respect to 0 degree centigrade. You can form a table like whatever we have seen in last question.
Hmm.
Okay, I think this will be
Okay,
okay.
okay, okay. Let me check. Let us clear this thing. So we have for 0 degree Celsius temperature is 25, 0.8 millivolt. Then when we are having okay, so we don't know okay we output
That is a
V
differential output voltage what we are having 2.5. So
yeah
we are adding that
2.5.
point 0.8
Only thing why we added that maybe is that the
because
compensation?
no, because we are already we want with respect to 0 degree centigrade.
Mm-hmm. When the
So
temperature
already for 25 degrees centigrade we are having zero point 0.8. So in order to
okay
know the then hot temperature, we need to add. That's what we have seen during lectures.
okay 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 what I thought this 20 the temp this voltage is already having since it is 25 so it is already having the effect of 0 degrees Celsius in it okay yeah this way also yeah it can be hmm. Okay. Yeah, that will work. Hmm.
सर
Yes, yes.
सर
Sir,
समझ में नहीं आ रहा है सर, वापस एक बार अगर आप रिपीट करो तो.
हाँ तो इसमें क्या so what he is telling see he is telling that for 25 degrees Celsius we had zero point 0.8 millivolt output. So now for some reference voltage 20, like for some for reference current this temperature 25 degrees Celsius when we set 25 degrees Celsius as the reference. So we were having see this one A into T minus A is basically Seebeck coefficient equal to some output voltage. Okay. So now what he is saying that this output voltage is basically because of the one mentioned here. The unknown temperature, the output voltage is 2.5 millivolt when the reference temperature is this. So he is saying this is 2.5 millivolt plus the reference volt, the output voltage when the reference was zero. Reference was 0 degrees Celsius. In this case, this was 0.8 millivolts. So if we add both this, so this is the total output voltage. So this is the total output voltage 3.3 volt for this 25 degree Celsius temperature. So now you got what he's saying, okay?
सर टी माइनस 25 क्यों लिया?
That is the difference, no? T is the we don't know the temperature, and at that point we have reference as 25. So this
सर
is the
रेफरेंस वोल्टेज पहले 0 डिग्री था, फिर
for
25 डिग्री सेंटीग्रेड हो गया.
yes,
तो सर इंक्रीज हुआ ना सर, वो
yes,
25 डिग्री.
yes.
तो हमने टी माइनस 25 क्यों लिया है?
No, no, that is the equation, no? See, uh, wait. This one, no? We are using this equation. This one. That is the
Okay,
out.
just
Ha.
okay, sir.
Okay.
Okay, sir. Okay.
Sir,
Yeah. Yes. Yes.
sir, from week 7, from week 9.
Week nine. Oh, week nine.
Yes, sir.
Okay. Week nine. I have don't have the solution for week nine. So till
Sir,
week eight, if you have any issues, then you can ask me from like
no, sir,
previous
I
episode.
just need some ideas, sir. I don't need a solution.
Ah, okay.
Sir, for average output voltage, we need to take the both cycles and we have to take the average, sir, for
Yeah,
fifth question.
normally it happens like this for both cycles, like full cycle basically. Not full cycle, you have to take the average.
Yeah, we have to take for positive half cycle and negative half cycle. We get a output voltage. With this, we need to get the average output voltage.
Yes, yes.
Okay, sir. Sir, I'm not getting how to find out the role of factor, sir. For question number 6,
Roll off.
role of factor, sir.
I didn't get
Role of
roll.
factor of the filter. In
Roll of
question number 6,
filters. Huh? Which one? Which question?
role of factor of the filter.
Uh,
Question week 9, question number 6, sir.
question. Question nine. The figure high
Yes.
pass filter.
No, no, sir. For week 9, question number 6,
Acha,
sir.
week nine. Okay, yeah. Okay, I don't right now. I don't. I haven't solved those this assignment because
No,
yeah.
no, no, sir. I just need a reference, sir. At least
I
how to calculate the roll of.
actually I don't know the acha. I don't know the question also. If you can tell me the question now, then I can at least help.
Yes, sir. Go to week 3, week 9, sir, and question number 6, sir.
Week nine. Wait. Let me open this. Wait. Week nine. Question. Which question?
Question number 6, sir.
Six. Okay. The roll off factor of the filter is. Roll off is
Yes.
basically acha. See, if it is a first order, this first order filter, then it is having roll off 20 degrees Celsius. It's like this. Okay. If it is second order filter, then it is roll off is 40 degrees, 40 dB per decade. So basically, whatever the order of your characteristic equation is, that is the order of the like the that the equation which you will be getting as the denominator. So you will so first you will have to calculate the V naught by Vi, the transfer factor, or you can I can directly you can say, since this is like there are two capacitors here, so what I think there will be its order will be two. Okay, you
Okay.
can directly say that. So like more the number of
40.
this capacitive and
Yes, sir.
inductive elements are there, based on that this order increases. So if there are two capacitors, then
Like
definitely it will be second order.
Butterworth filter approximation, sir.
Uh-huh.
The same way.
Uh-huh.
Butterworth filter approximation, first order and second order. There also, with respect to the capacitor, we will find out the order, no, sir.
Uh-huh.
That is S square 0.707 into that one omega
So
n.
yeah, I completely didn't get your question. You are saying,
Yes,
can
sir.
you write if possible?
Sir, Butterworth filter approximation, sir.
Butterworth, yeah, Butterworth.
In this Butterworth filter approximation also, where we will find out the order with the same approach, no, sir. I'm
That
correct
we
in I'm
that
correct.
what yeah. You were talking about what we studied in lecture, no? That Butterworth and all. Butterworth we didn't study.
No, sir.
But simple thing is that if you have that the role of factor of the filter is, so you need either you can go with proper, you can calculate the proper. Okay, I will say you can either calculate the proper transfer function of that thing, then you will be able, after analyzing the characteristic equation, you can get the order of that. And if you get the order, then you can get the role of factor. If it is second order, then the role of factor will be 40 dB per decade. Okay, if it is first order, then it will be
Yes, sir.
20 dB per decade.
Sir,
Yes,
one
sir.
more thing to answer his question. So I'm having that simulation. So
Which
is it
question? Which question?
that week 9 and question number 6?
Acha, week 9. Yeah, yeah. Tell me.
So, if possible, I will share my screen so that I can
Yeah, yeah, yeah,
explain
you can
quickly.
share. You can share. Yeah, Arjun. Yeah, sir is there. Yeah, I have. Yeah, Ramurti, you share your screen. I will answer Arjun. Yeah, is there a person watching recorded live sessions? Yeah,
Okay, okay.
I gave that YouTube link in that discussion forum. So I will again update that link so that you can see all those
So, is it
recordings.
visible, sir? Is
Yeah,
it
it is
visible?
visible. Ha, visible.
Okay, so this is the question what he is asking.
Ha, okay.
So I'm already having that simulation. So
Hmm.
here we can see when we are doing AC sweep,
Ha.
so we are going to get the frequency responses like
Okay,
this.
okay,
So
okay.
okay, so in y-axis is in decibel. Okay,
Ah,
okay.
ah.
The decibel means let us consider first point is 1K frequency. The next point is 10K. We
Hmm.
can see that approximately the response magnitude responses keep on decreasing from 0 to minus around 23. Anyway, it is approximation board plot.
Hmm.
So we are taking it as 20 dB. So next decade, that is 10 into 10, that is 100K. We will see
Ah.
20 to 46.
Okay, okay, okay.
Okay, the response magnitude is keep on decreasing up to 100 10 mega. Okay,
Hmm. Hmm.
so that's why it is known as that
20 dB per decade.
decade minus 20 dB per decade.
Okay, yeah. I'm saying normally it happens like if you have two capacitors or two, like normally we have second order. But since this is, I think, this is a band pass filter. So sometimes the setting of these capacitors are such a way that they will be nullifying their effect or something. When you will find the transfer function, you will be able to know it is not 20 dB per decades. That's what we can see in this thing. So that's why it is good to solve for the transfer function. So you will be sure that. Okay.
Okay,
So
shall I
yeah,
stop sharing?
yeah, you can stop
Okay,
it. Uh,
okay.
so yeah, Thalpasai, as you were saying, we can directly say also from the number of components, like whether it is second order, first order, but just to make sure, because there can be the positioning of these passive elements can be in such a way that it is not necessary that it will be a second order system or third order system, like that, based on the number of components. Okay, so it is better to go for the transfer function. So Ramamurthy, you solve this. So I will just suggest you to go and just try to solve for the transfer function also, because in exam you won't be able to simulate and then solve it. Okay, if this question comes like that, है ना?
So
So
one more small request, sir. So
yeah, yeah.
sometimes in weekly assignments we are getting questions from the topics which is not covered. Okay,
Okay.
it's like transfer functions, all those things.
Acha, you okay, okay.
Okay, some time it is advancedly asked. Like week 3, we have questions on week 4 topics like that. So
Oh,
kindly look into that matters. Also, one more request. Could you please have a session on PID controller design and other things more precisely, because integral control we did not cover. I think so. So
okay, okay. So yeah, acha, you need a special like time for PID, na?
no, PID tuning from transfer function to how to convert the
Got it.
real.
Okay, I can do one thing. Maybe next I can devote maybe 45 minutes something. I will so I will give some time for this opamps what we assignment questions, and rest of the time I will give for that PE. So we'll start from PE controllers, then PD controllers, PI controllers, then PID controllers, and why we
Okay.
need each and everything. We will go through that.
Yes, sir.
So we
Thank you.
can do that. Yeah, I will record the session next time for next week. Okay. So I will. Yeah. Okay. Yeah. I also think about controllers. Yeah. I think you should be knowing more about that and how you can realize those things using options. Yeah, I will do that. So okay, I will write something. Wait, maybe in the top. Yeah. Okay, so
Sir,
one thing. Yeah. 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 Tell me.
sir, sir, for amplifier, the gain should be greater than 1 or equals to 1 in some cases.
Amplifier. See, when
Yes,
we
sir.
say amplifier, so we are saying it is gain equal to 1 or greater than 1, but op-amps can attenuate also. So, normally we are saying amplification, but normally people say amplification for both things. Like if it is gain is less than 1 also they say like okay, but it is an amplifier like that.
It means that it can be greater than or equals to 1, sir.
Yeah, greater than 1 also equal to 1 also.
Okay,
But
sir.
since it is when it is equal to 1, so it is not amplifying basically. If we go in a literal way, literal sense.
Means in week 7 question, in the last question, sir, week
Acha,
7,
yeah, yeah, I will
they
tell
are
you.
asked about error amplifier.
Week 7, last question. This
Yes,
one,
sir.
this one, 10th.
12th,
Oh,
12th.
sorry, week 7. Okay, week 7. Okay, I will just open it here. Week 7, last question. Wait.
For all the amplifiers, the gain is 1, sir.
Okay, okay. Select the suitable opamp-based
It,
error amplifier configuration. We can say that it is, yeah. Yeah, that's what. Amplifier term is now used for most of these, like whether it is gain 1 or like not 1. So
okay,
it
sir.
is, you can say it is a, what we say, a convention basically, when we say an amplifier. So, but the gain can be 1 also. Okay. So, yeah.
Okay, sir.
uh,
Sir, next, how to access the recording lecture, sir?
Yeah, I will share that YouTube channel link again in that group. Uh, okay, then PPID. I will share you. You will get the notification. Just check the discussion forums. I will share that link. I'll share that link. So there are all the,
Recorded sessions also, sir.
yeah, recorded sessions. So anyway, you have the
Okay,
access to main course content. What we do on Tuesday, those all video lectures are. I will give you that YouTube channel link so you can see that. So I will just suggest if you don't want to see again this what you have been what you have learned in this weeks, then you can directly skip to the after 1 hour you can see these videos, because normally I am either solving the assignment questions or I am solving some extra questions, and those extra questions are really good. So you can get more idea about these op-amp applications and all. So you can directly skip after 1 hour. You can see those videos if you don't want to see
okay,
again
sir.
this. You don't want to revise these things. You can directly skip after
Okay,
one
sir.
hour. You can see
Sir,
the
and
videos.
in the
Huh.
final exam, the questions means the question format can be expected as what, sir? Like
So,
in the conceptual or problems or problematic.
you see, it can be both. See, whatever the pattern sir is following in this assignment questions, so he will be giving in that pattern. It can be conceptual. It can.
Similar to assignment, sir.
Yeah, yeah. It can be theoretical, practical, applied also, some designing based question also. It can be there, but I'm not sure. But I'm only saying based on the assignment questions. So normally it is the thing which
Okay, sir.
which is there. Yeah,
Okay, sir. Thank you.
yeah, yeah. So this next lecture 1 45 minutes will go through this thing. PPID controllers and all those things. So you can join the live session or you can see the recorded lectures also. Okay. So yeah. So yeah. Apart from this, anyway, I will be continuing because since others can see this recording, so I will be continuing with the normal what we were being taught in this lecture. So apart from that, if you have any other doubts, you can ask me. Otherwise, I will start. Okay. Yeah. I will then send you the link. YouTube link for it.
Sir,
Yeah. Tell me.
sir, can you post the link now itself, sir, in the comment
Okay,
section?
okay, wait. I'm waiting. Wait. Just check me if you are able to see the videos there. If somebody can check. Yeah. So are you able to access this? Arjun, you were also asking for this now. Can you access that? Okay. Yeah. Okay. Fine. So yeah, this is the I anyway I will post it on that this also discussion forum. Okay. So we'll start with our thing. We'll continue with this thing. So yeah, we saw that we'll be requiring the same sensitivity because otherwise we will be measuring the same output for 110 as well as 100 degrees Celsius. So that is there. Okay. Now, so now we saw this also. Okay, I will present this. So we saw that. So we constructed then opamp circuit. We realized this thermocouple thing using opamps as so we had this opamp here, this thermocouple here with this junction. Okay. So by the way, when is your exam? Anybody can tell.
Sir, 28, 29, and 30 April.
Oh,
3 days
three.
are there,
Huh.
but not allotted yet.
Okay. Okay. One day your exam will be there according to your slot, based on your
Yes,
preferred
yes,
slot.
yes.
Okay. Okay. Got it. Okay.
Any of one days.
Okay. Got it. Got it. Yeah. So yeah. So we have this thermocouple. This is TM. This we have basically grounded. That means this is having reference as 0 degrees Celsius. Okay. So and we have this one. These are the junctions where across which we are basically calculating the differential voltage, and this is resistors. This we chose as 570 kilo ohm, and this was 2.34 kilo ohms. So in order to maintain that gain of 244, so we are getting some output here. And for compensation, what we are doing, so we are using LM35. This is basically a dependent voltage source. So this is depending on the this reference voltage. So we are reference voltage is being fed here, or it is sensing the reference voltage. So let's say if it is 0 degrees Celsius, it will do nothing, है ना? But if it is changing, then it will compensate that by adding that voltage. So here it is 10k. So now then we are using an summer amplifier. Yes, plus. Okay. So finally we are getting 2 volts here. We are supposed to get 2 volts. So basically this while we are adding this, so how it is helping this compensation compensating circuit. So let's say if we have reference at 50 degrees Celsius, not at 0 degree. So we reference and we have the hot junction temperature as 200 degrees Celsius. So according to this thing, according to compensation, here also it should show 200 only. So what will happen? 200 minus 50. This is the difference of these two junctions into the sensitivity factor. We are getting 6.1 millivolt. Okay. Now after, so this 6.1 millivolt. So this is we got at the differential output of the thermocouple. Then if we amplify this thing using the amplifiers used here, then we will get 1.5 volts. So what is happening? This 1.5 volt is basically, since our output is what? Our output is 2 volt per 200 degree Celsius. 2 volt for 200 degree Celsius, as we mentioned here. Uh, yeah, 2 volt at 200 degree Celsius. But here what happened? We were measuring 200 itself, but instead of 2 volts, it was showing 1.5 volt. That is equivalent to 150 degrees Celsius. So it will show 150 degrees Celsius, but we actually need 200. So how will compensate this thing? So now if we can add 1.5 volts, the 0.5 volts, then what will happen? Our output will become 2 volts. So this 0.5 volts is being added by this LM3. This is LM35. So what it is doing, it is having a sensitivity of 10 millivolt per degree Celsius. So for let's say 200 degrees Celsius, what will be so for 50 degrees Celsius of reference temperature, what its output will be? It will be 50 into 10 millivolt. So it will be basically zero point 0.5 volts. Okay, volts. Yeah, volts. So it will be zero point 0.5 volts. So LM35 sends the reference voltage. Now it changed to 50 degrees Celsius. So it sends that voltage, that temperature 50 degrees Celsius. Then accordingly it sets it, this is the dependent voltage source. So accordingly it creates its output as zero point 0.5 volts. Now this zero point 0.5 volt is being added here. So what so we were initially we were getting 1.5 volts. So after adding this zero point 0.5 volt, we will get final 2 volts. So ultimately, what we will be understanding that okay, 2 volt is the output. So that means we are getting 200. We are basically measuring 200 degrees Celsius. So this basically LM35 made the system immune to the changes in any reference any reference temperature of this cold junction. So this was cold junction. Fine. So this was the yeah, this is the example. This is the like application of this compensation circuit. Hmm. now now we saw that we can use INA also instead of like directly we can use INA. INA can be used. Why we can use why we need INA? Why we shouldn't use INA? Because first of all the circuitry will be easy. Two inputs we will be giving. Okay, that junction input, thermocouple junction input. We are having a reference pin here. We are having an output here. We are having one RG here, which we can set the gain. So this reference input, if we so basically whatever like so internally it will be compensating this reference whatever the temperature that voltage is there at the reference junction, and it will be like it will be INA will be having very high CMRR. CMRR will be very high, and this what we say uh, easy to make this, but mainly this it is having very high CMRR. So that's why we can use this, and yeah, bias currents and all those things are also less in this INA. So we can use this INA circuit instead of going with that this previous op-amp circuit. Okay. Now we are done with this part of experiment. Then we studied about another experiment, that is EEG based experiment. So second experiment what we learned was it was to design and build an op-amp for ECG signal acquisition. con- for signal acquisition, and then we need to do its conditioning and at the same time processing, so that we can ultimately get this ECG signal. So now so the question must arise that why we need this like what we say this much of processing in this ECG signals. So if we talk about few of the medical purpose signals, signals which are used in this medical field, or the techniques so I will say, so ECG, we have ECG, we have EEG, electroencephalography, then we have electromyography, then we have electroretinography, electro-ophthalmography. Yes, this much of these many graphies. So these frequency range, the signals of these are. So this is just for the knowledge. This table I'm giving to you, so that you can see, okay, these kind of signals these are there and how much amplitude they are having. That's why we need so much of complex circuitry to actually extract that signals. So signal amplitude. What are the signal amplitude? Okay, and the yeah, that is fine. Signal amplitude. So this is basically 0.05 to 120 hertz. This you studied in lecture also. Then EEG is zero point 0.1 to 100 hertz. Then the signal from muscles is 5 to 2000 hertz. It can vary. Then for ERG it is 0 to only 20 hertz. And EOG can be DC to 100 hertz. Okay. So now, but the thing to look for is that their signal amplitude. So it is 0.125 microvolts. It is in this range. See how much less this signal is. And then it is for EEG it is 2 to 200 microvolts. Then we have 0.1 to 5 microvolts. Then we have zero point 0.5 microvolts to 1 microvolt only. Then we have 10 to 3500 microvolts. So when we are measuring this much less value of amplitude, then we will be definitely needing so many complex things, complex circuitry, so that we can actually extract this thing, because these are prone to many noises. Noises can be from environment also. Noises can be from artifacts. Artifacts are very important thing in medical line. Artifacts are basically when you are taking. So you must have observed when you are taking this. Let's say you are taking BP, blood pressure measurement, then you are breathing also. So you are breathing, so your muscles movement is there. Or when you are taking the ECG itself, so you have connected some electrodes near your heart, or there are many techniques to connect electrode. Then you are breathing, you are moving also. Like many things are happening. So all those things are creating some signal, creating some output, creating some noise also. So these are also there, and these values are near to them only. So then also we need to extract these signals. It's basically very difficult process, but at the same time very interesting to look like how we do these things. Okay, so I gave you a okay broad idea. So why we need these signal acquisition, conditioning, and processing techniques, because their magnitudes are very less. Anna. So then for this purpose only we use INAs here, because they are very highly immune to noise. And then in this experiment we wanted to detect the QRS detection. That is the so this is basically the wave. It looks like this. So this is PRT, this is QRS. So this segment, if we so this is QRS segment, and this is PRTU. Okay, so this we have to this we basically, if we so we wanted to detect BPM also, bits per minute. So if we can detect these things like this wave itself, then we can get okay this much of beats are like it's beating this much of per minute, this much beats are there in per minute. So all these things we can calculate like bpm qrx complexes. Okay, and the frequency of this complex is around 70 hertz.
Sir, one more doubt, sir.
Yes, yes.
Sir, normally the common mode ratio means it is not going to accept the common mode signal. So whatever we are getting ECG, ARG, all are common mode signals. So in that case, whether we need to go for low common CMR ratio amplifier or
uh,
some other
who
or
no
high.
no who said that that is common mode?
So CMR or common mode
No no no
electric.
that ecg signals are common mode, who said that?
Yes, because in lectures we are having one ground, common ground, then we are getting different.
So we are basically calculating difference now of two
Yes.
things. See
Okay.
that diagram which you saw in that lecture, something like this. So one electrode was giving from here. We are giving some like another electrode from another hand. Okay. Then we were giving it to the input of this INA. See, these are two different like put it. This is basically as INA is detecting what difference now. So it is the difference of this potential of this hand potential and this hand potential. So this is V1, this is V2. Got it? So this is there. So we are but if noise can yeah, so for noise and all that will be common to both the signals. That we have to reject. That's why we go. Please can anyone share recorded lectures? Leave suddenly my meeting went
So
down.
always we need to go for high CMRR
Yeah, yeah.
for
High SMR.
all these kind of
Yeah, every time we need high SMR because noise is same for this channel also, same for this channel also. It is matlab, yeah, it is same for both. So it will be interacting with both the channels and the same signal, almost same signal will be interacting like that. So if we can remove that thing, so that's why we need high CMRR. Okay, but here we are basically measuring difference of these two voltages, that they are from these two hands. Okay, and we reference this. So yeah, so this yeah, so I'll make this full circuit, this thing. So this is basically a wire which is connecting this INA, and we are using a low pass filter here because as we saw, okay, this our signal can be high also. It is so that's why we are using because we need at least we don't need less than 17 hertz signal because QRS complex is that. So that's why we are using low pass filters. Okay, this is there, and then we can use this RG for INAs to basically vary this resistance plus minus. It's basically gain of this INA 4.7K 47 picofarad. And yeah, so this is there. I will add some page. So this is basically circuit. So now as we talked about that pre-processing. What is pre-processing? For pre-processing, basically we are filtering lots of noises. So one noise is power line interference. So in this, we know that in India it is 50 hertz, and so it can be removed by using uh, yeah, it can be removed by using a low pass filter of 100 hertz. Wait. sorry, notch filter. This can be removed by notch filter. Okay, so then there is one more noise from electrodes. As we are using these are contact methods, so we will be using different types of electrodes. So electrodes can pop out, or electrodes can change their positions. So, and the contact they are making, the contact they are making with the skin, that all that can also, they are making with skin, that can also introduce some noises in this. So if for the, yeah, so yeah, contact that they are making for this from the skin, so this, that is also an issue. Then as I said, the artifacts as when we breathe, when there is small movements, and because breathe we cannot stop, and there are many involuntary movements. Because of that, our body is changing its shape at continuous interval. So for that, like we need to reduce these artifacts also, and this is basically less than 1 hertz. So for that we need a high pass filter which is having a cutoff greater than 1 hertz. Okay. Then there can be baseline wandering, that is addition of offset in the in our signal, baseline wandering. So it is basically this is near 0.1, 0.5 hertz or something. So because of this, some offset is introduced. So instead of a signal looking like this, it will look like something this, overimposed on some offset. So it can saturate also if our supplies are not enough, power supplies are not enough, so it can saturate this thing also. So it will look like something like this if the offset is increased. This is normal, the negative circle. But since output voltage is limited till here, so we will get a saturated uh, output. So these things we have to remove. So for that we can go for first we can go for LPF design. So since we don't need yeah, actually a notch filter also we can use, or acha. So so for low pass filter we will use this cutoff as 108 hertz. So after that so basically after that it will the cutoff will be, after that it will not be in taking any of the signals. So low pass filter, as we all studied, we can realize simply using a capacitor R2, this R1, this thing. Okay, this is V input. So the gain of this low pass filter is 1. Hmm. So according to this, and according to this formula, 1 by 2 pi f, sorry, RC, we can find the R, this FC. If we choose any of this value C, if we want to choose, we can get the R if we need this 108 hertz. Then we have HPF design, high pass filter design. For basically its cutoff, we keep it at 1 hertz. Okay, so this is as in lectures also it was mentioned that this is of it is having a high roll off, that is 40 dB per decade, I think. mm, as it is having two capacitors, but that we cannot be sure every time, we cannot be sure about that, as we just saw. Okay, V out is this R2, this is R1, this is R3, C1, C2. So this cutoff is given by 1 by 2 pi under root of R2 C2, yeah, and R1 C1. So this we can limit it to 1 hertz, and then we have notch filter. So which will be removing this 50 hertz interference signal filter. So notch filter, it looks like something like this. We have this capacitor. So we have circuit like this for notch filter. So we have accordingly this values, that is 1 by 2 pi r1 c1. Okay, and we can get this 50 hertz, and accordingly we can calculate r1 and c1. Yeah. So these are filters, and then we also use half wave rectifier because half wave rectifier we don't need the negative cycle of this PRTU, this waveform. So we will be getting only this one, something like this, PRT, something like this. We'll be getting, and realizing an half wave rectifier is easy. This is 100 kilo. This is what. Okay, this we studied. This is all now. So whatever we studied, now we are applying that thing. Half wave rectifier, this notch filter, HPF, LPF designs, and all those things. So basically, we are doing the pre-processing, and now then we also saw that we need beats per minute. So for beats per minutes, basically we are detecting R. So for BPM, detecting R. Okay, R detections. So this will be, here we will be using a peak detector. So this will be a diode connected, the input connected to the output, and we have a capacitor here, and then we are giving this voltage 2 mega ohm. This is 1 mega. Okay, this is the input voltage. So in this case, as the this capacitor will keep on charging. So once so let's say we were having this signal, so we had voltage something like somewhere like some at some position here, so it will be charged till there. So but it will only be then this voltage will be high, so this will be open. But once if we get this the input voltage, this R, this voltage becomes higher than this set voltage, then again this capacitor will start charging, and it will the voltage across this capacitor will be more. So accordingly we can get this output at that accordingly we can get the output, and this will be so then whenever this R will be there, so once it achieves the voltage equivalent to the R value, this voltage, after that whenever the R, that R peak will be coming, only then it will be getting we will be getting some output here. If the voltage will be less, then this capacitor will not be having any effect. If the voltage will be there itself, then it will be charged to that voltage, then we will be getting some output data here. Then we can use one trigger unit. So basically here we are attaching one that we will see in this next week, like how this trigger unit will work. Okay, so it is something like this. So basically we are using a comparator here.
Sir,
Yeah, yeah, yeah.
sir, my question is, draw a half a rectifier, no, sir,
Uh-huh.
upside.
Yeah.
through diode
हाँ
BPM detecting. Yes, sir, of a rectifier.
हाँ
Sir,
this
could you please explain? Yeah, sir, could you please explain the operation, sir? When it will be conducted, the diode will be in a conduction.
okay. So let's say okay, I'll circuit and try this. So we have something like this. This is VA. Okay, we are let's say we are getting some waveform like this. For positive cycle, so initially, any op-amp circuit works as a comparator. After that, it realizes where if it realizes okay, this diode is on or off. Based on that, it follows that proper negative feedback circuit. So initially, we will think okay, it is acting as a comparator. So where here we have V in, here we have zero voltage since it is acting as a comparator initially. So what will happen when we are giving a positive cycle? So this non-inverting terminal voltage is higher than the inverting terminal voltage. So this will be plus V set. So since this is plus V set and we are giving this at the cathode, sorry anode this diode. So it will make it forward bias. That after facing this, then what will happen? Then this op amp will act as a negative feedback for the voltage follower. So then we can remove this thing. We can remove this diode, and it will be acting as normal like voltage follower. So this zero voltage will be gone. So this V in will be replicated here. V in. This is V in here. So we are getting whatever we were giving. We were getting similarly as like that at the output. This is V naught. This is V input. Okay. Now in case of negative supply, again we'll see. Again we will make this as a comparator. We'll think okay, this is acting as a comparator. So then what will happen? This is 0 volt, but this is negative now. So this non-inverting terminal voltage is less. So this 0 voltage is there. So this will be minus V set. In that case, this diode will be open. This will be acting as open. So since this diode is open, so there is no concept of virtual short here. So there is no concept of voltage follower here. So there is no V in here. So we will be getting zero voltage for the negative speed for negative cycle. So that's how this outdoor rectifier works. You got it?
Yes, sir.
Okay.
Sir, if a voltage drop is present at, for example, if it is
Yeah.
germanium,
If it is
uh,
if it is okay, let's say voltage drop we are looking at
it is germanium, it is 0.3 volts now, sir.
zero point
13
3
voltage.
volts. Yeah, silicon is 0.7. Yeah,
Yes, sir. The same voltage will be present in that non-inverting terminal, sir.
that wheel.
Yeah.
No, no, no.
Yeah. I mean, if it is voltage drop is present,
Then
I
also
mean,
wheel will be following this voltage, input voltage. Only thing
okay,
will got it.
the
You
drop
see,
doesn't matter.
drop it will why these things are called precision for yeah precision whatever the spelling is of precision rectifiers because it is not dependent on this. That's why we went from normal rectifier. We use this normal rectifiers, no? You have seen this these circuits, yeah, something like this. We use,
Yes, yes.
है ना? So why we chose op amps? So because this is solving the problem of this diode voltages 0.7 volts or 0.3 volts because this voltage see if we give less than it will defect only when if we have let's say silicon diode is there but if we are giving 0.5 volt supply here minus 0.5 volt first of all it will not work if it is working then this plus V set will be plus 0.5 volt so it is less than 0.7 volts then it will not work but normally we have plus minus 5 volt supply. So in that case it will work. This drop will not be having any effect.
Yes, sir. Getting this, sir. Getting it. Thank
Okay.
you.
Yeah. So I think this much is there for today's thing. So if you have any doubts, So just tell me. Otherwise, yeah, I had one. Yeah, I think Ramamurthy only asked me that if you need some guide for the thermocouple measurement. So I have shared one book in that session, and yeah, and one book and one this also. This is also there a basic guide to thermocouple measurement, but this is quite deep as although they are telling about these what severe effect is and these types of thermocouples J, K, T, E, S. You are studying this is the thermocouple response as we studied. This is what we talk what we say that alpha, that is Seebeck coefficient, and then you don't have to go for these equations, but then you can get an idea. Okay, this is a grounded thermocouple. This is having ungrounded thermocouple. So these are all types. So you can get an idea of how these things are. And but I don't think. But if you are really interested, you can go into these circuits. Like so, when you are using a thermocouple, so if you will be using these resistors, so it can pull down bias resistors. So all these why they are used and for what purpose. So I've shared this PDF in that your discussion forum. So this is there. So and I've also shared one book link also, that is principle, that is measurements and instrumentation. So there also you can find some lectures about this, some chapters about this thermocouple. So you can look into that also. Hmm. So this is the. So if you have any other doubts, you can ask me. I think that session that the content is over. Today I don't have any extra questions. Yeah, but if you have any doubts, you can ask. Like any assignment questions till week 8, if you have any doubts in any assignment question, then you can ask.
Sir,
Yes. Uh,
sir,
yes, yes, yes.
could you repeat again the diode voltage thing, sir? I'm getting a little bit confusion, sir.
Diode voltage, which one?
Yes, sir, that a halfway rectifier, that
Oh,
cutting voltage.
this one, na? Should I tell you again?
Yes, sir. Yes, sir, exactly.
Okay, okay, wait, wait.
When cutting voltage is present,
So see,
I mean,
when I said that, just think that initially it is acting as a comparator. So if what comparator's output is either plus reset or minus reset. So we are giving some, let's say, plus minus 5 volts. That is the supply voltage to this op amp. So when diode is like this, we are talking about the first positive half cycle. What will happen? Now this is positive. This is positive. Now initially it is acting as a comparator. This negative inverting terminal is having 0 volts. So what will happen? This non-inverting terminal is higher than the inverting terminal. So this will be plus V set. Till this point you are clear now.
yes, sir. Yes, sir.
Then this plus V set is what, 5 volts. So this 5 volts is obviously greater than 0.7 volts for silicon or 0.3 volt for germanium. So it will make this diode easily go into forward bias. Got it?
Yes, sir.
So that's why it is not being affected by the supply, this reverse bias voltage of this diode.
Okay. Sir, if it is exactly the cutting voltage, then it would be off now, sir.
Then so that's what, again, then what I said. If our supply is, let's say, plus zero point 0.5 volts and minus zero point 0.5 volts,
Yes, sir.
if this is the case, then plus Vset is what, plus 0.5 volts. Okay,
Yeah,
then it will not be open in case of silicon.
Yeah, it will be a off condition
But
according to me.
normally we don't use this much of less supply. We normally use plus minus 5 volts. Okay, because there is no use of using this much less supply, because our output will not be able to go beyond that point 0.5 volt. So that's why we don't use this much of less supply. 5 volts and minus 5 volts are the minimum supply we use, and we normally have this in our even like any DC DC that, yeah, DC generator or something.
Getting sir. Yes.
Yeah. So any
Sir,
other doubts? Yeah.
no, sir, everything is perfect, sir. I have one doubt. I mean, not getting the idea, sir.
In which
Just
doubt?
my
In which
estimate is correct
your
or not?
voice?
If anything is required, week
Where?
9, sir.
Week
Week
9.
9.
Okay. Week
Week
9.
9 question number 8, sir.
Question 8. Week 9. Okay. Let me see. Week 9. Question 8. Week 9. Question 8. Ha.
Sir,
Okay.
when can you question? First, I need to find out the output voltage for U1. With that voltage only, I can able to proceed now, sir. My
Yeah,
approach is
yeah.
correct, sir.
You can go with that. Consider opamp is already supplied. Okay. Compute the output voltage YouTube.
Yeah,
Or
by using the
Hmm.
by using what U2, if I go through 0, then if I find out the output voltage of U1, that output voltage with this I can get a current, right?
Yeah, you can get the current. Yeah.
With this only I can able to find, sir. There is no another way, alternative way, no, sir.
No, no. This
Is
is
there any
fine. I
al-
think.
Okay, okay, fine, sir.
Yeah,
Yes, sir.
this is
That's it,
fine.
sir.
Yeah.
That's it, sir. Thank you, sir.
Mhm. Yeah.
From my
Okay.
side. Thanks, sir.
Yeah. Okay, then if no other questions, then we'll end this session. We'll discuss week 9 questions in next week. Okay. Yeah. Thank you.
Yeah, surely, sir.
Yeah.
Surely, sir. Sir, if you don't mind, can you keep that question, that the standard book in chat box, sir? I will copy it, sir. Since I have to
That
go.
I don't have the link. I don't have the link for that standard book. Okay, wait. That this opamp standard book, no?
Yes, sir. Open standard book, sir.
Okay, wait. Mm, yeah. This is the name of the book. Sergio Franco designed with operational manual.
Yes, sir. 1 minute, sir. I will copy it.
Uh,
Yes, sir. 1 minute, sir. Thank you, sir. Thank you.
yeah.
Thank you,
Okay.
sir.
Thank you.